Good morning, good afternoon, good evening, depending on time zone. This is really Wang from Mass University. This session, we have two speakers. Let me introduce the first speaker, distinguished Professor Lu Jie, is an Australian Literate Fellow, IEEE Fellow, and IFSA Fellow. She's an international renowned scientist in the area of computational intelligence, and she is the director of the Center for Artificial Intelligence. And so she also associate dean in the Faculty of Engineering and Information Technology at University of Technology, Sydney. Let's welcome her to present the presentation of prediction and personalization. And in this talk, she will focus on the detection and adaptation of unforeseeable change in streaming data distribution, called the concept drift, to increase prediction accuracy and recommend system technology to support personalized services. Now let's welcome distinguished Professor Lu. You can start your presentation now. Yes.
Okay. Thank you, Professor Wang, for your wonderful introduction. Thank you, everyone, to participate in my presentation today. My talk today is about prediction and personalization. I believe personalization and prediction are the two key AI technologies for future of finance. For prediction, I will talk about in the very difficult situation. Data is in streams, so we call streaming data. And the situation is very dynamic. That means fast change. And so the data distribution has the distribution fast change over time. And also we want to keep a very good prediction accuracy. And in the personalization, we consider we have a massive finance product or services, and the different person needs some personalized services and recommendation. So we will introduce recommender systems and to support personalized services. However, we are in the big data at the same time, data sparsity problem. And also we have a new user issue. So my talk today covers the two directly linked areas and also deal with the very challenging situations. We talk prediction first. We consider the data is not collected in a database. It's data streams, no ending data streams. And the data distribution keeps changing. So that's what we consider it's a status in that time, in that type of data distribution. And we have a dynamic situation that has a data uncertainty issue actually involved. We all understand we may consider data and to use data to support prediction or decision making. Actually, we need machine learning. So machine learning will learn from data, then generate some results, which is used for prediction or decision making. That is my start point today. So data are in different scenarios. We have a very high speed data in streams, high volume, and also multiple data sources. Machine learning, we understand, machine learning actually are algorithms or models. That machine learning learn from data, generate whatever classification, this regression, aim to support prediction and decision making. We want the prediction to be fast, to be accurate, and to meet our decision requirement. In general, data, we have a structured data, we have unstructured data. For structured data, we collect it into database, for example, and the unstructured data could be some image data and graph and streaming data, also one kind of unstructured data. That is our today's talk we focus on. And what are the difference to process those data? If you have static data, then you do machine learning or do data analysis, and you have assumption. Training data and the new coming data actually are in the same data distribution. So you collect the data and do training and then get models, and models can be used to, by the new coming data, then generate the prediction. So in such a case, you can say that's data all in same distribution. So you use the first 3 branch of data, generate a model, which can be used for coming data. However, you see the dynamic model. In the dynamic model, the things are different. The things become to, you use the first group of data, generate model 1, but if you use model 1 to have prediction for new coming data, when the new coming data become to different in different distribution, then the model 1 doesn't work anymore. So you need to train another model, that's model 2. Then work for a little while, and the data distribution has another significant change. So you have to use model 2. We know every time we build a new model, and we need to know when is the time to build a new model. What is the time the old model doesn't work, and how the new model to be, and also this high cost. And what is the concept drift? The idea is when you have the old model, that's one concept, and then when the concept has been significantly changed, that's what we call drift. So you need to have a new concept. I will give a little bit more details about the concept drift. To understand the concept drift, to understand the data distribution change, I just gave you an example. We have been using mobile phone for many years. Think about 20 years ago, when you have your first mobile phone, or even 10 years ago, mainly your mobile phone is used for call your friends. And later on, the usage has been changed. Maybe we use 20% of the time to watch news, and another 80% to make a phone call. How about recently? Probably 40% of your time to this use multimedia to talk to your friends, and also 10% play games, maybe 15% to watch news, and 10% use Google Map, and then only maybe only 10% or 20% used for phone call. That is a usage, this customer usage of mobile phone has been significantly changed. Consider usage is a stream. Then in such case, if you use the model established 5 years ago based on that time customer usage to have prediction about today's customer usage, I believe that could be accurate or there's a good prediction. So that is an example to show us the usage has been changed or the usage distribution has been changed over time. We understand machine learning. For machine learning, normally we have raw data, then we do some process, then we learn from data and to find some patterns. Those one we are used as knowledge. When you have new data, we just use the knowledge to support decision making and prediction. So machine learning itself is a computational process to discover patterns from historical data that used for new data. But as I mentioned before, we have assumption. The assumption is historical data and new data have the same distribution. But we consider the mobile phone example. Historical data and new data have a different usage distribution. In such case, you cannot directly use the model generated by historical data. Otherwise, you cannot get accurate prediction because the data distributions are different. So in such case, we consider concept drift. We can say in that model, we use the first data to train a model 0. Then we use model 0 for the second, third coming data. And we realized in such a situation, we have a very high error for prediction. That means the model doesn't work anymore. That means we have a concept drift happened. Same situation, when you use new model 1 and only use for a little while, then that's what we call concept 2. And here you can see very high data errors, very low prediction accuracy. That means you need to use a new model. That is we call concept drift. That is the drift time you need to detect. And that is a new model we call drift adaptation. There are 4 main types of concept drift. One is sudden change. And also we can say we have a different other types of change. And the last one quite similar, quite like the season. So like this winter, summer, winter, summer. That's also one type of concept drift, from sudden to incremental. Some algorithms can be used to deal with all types of concept drift, and some algorithms or machine learning or drift learning method only deal with 1 or 2 types specifically. And when we talk about concept drift, normally we need to consider 3 parts. 1 is drift detection. 2 is drift understanding. And 3 is drift adaptation. For drift detection, just as I mentioned, that you have data, then you test, there is drift, yes or not. Of course, you need an algorithm to do detection. And when you say, no any drift happened, then you can still use previous classifier, for example, to continue your learning or continue your prediction. That's a drift detection. And when you have this detection to identify drift happened or not, if you found it, that it's a drift happened, yes, then what you need to do, you need to do drift understanding. What does it mean, drift understanding? You need to know where is the drift and how big the drift and what happened or what caused the drift. All the related issues you need to consider. And after that, we have a drift adaptation. That's we will discuss later on, how to get model 2, model 3, and so on. That means you need to update your classifier. That's the original model you established. And this, after that, you can get good this output. So 3 components in concept drift framework. 1, drift detection. 2, drift understanding. And 3, drift adaptation. We have 2 main strategies to handle concept drift. One is lazy strategy. The lazy strategy, actually my talk today is focused on lazy strategy. The lazy strategy, the idea is always do detection to say drift happened, yes or not. If yes, then we think the way to update model. But the 3 ways to update model. One is retrain the model. So we do drift detection, happened, yes, then we return the model to a new model. Could be totally different. That's one way, we know high cost. And the second way, we also do drift detection. Then, and we don't build a new model. We just adjust the model. So in original model, we change some parameters or we change a little bit of component. The third one is drift detection first. After that, and we don't adjust the model, we adjust the prediction. So that means we can change the input or change the output. So anyway, all the 3 methods are under lazy strategy. What does it mean lazy? That means we do detection first. So I can give you an example, just like we have a cleaner. The cleaner come to the room to clean the room. And she has 2 strategies. One, she go to everywhere of the room to check dirty here or not. If not, don't do anything. If she finds somewhere quite dirty, only clean the little where. So that is the idea of lazy strategy. The second strategy is the active strategy. That means the cleaner every day morning, 8 o'clock, comes to the room and do all the cleaning without checking where dirty, where not, just clean everywhere. That's active strategy. Normally, we don't do detection, right? Just like cleaner, don't check where it's dirty. Directly do incremental learning. That's also directly do adaptation. And second, example learning, put multiple these models together. And another one, active learning. So those three also can be used to solve concept drift, and this don't need to do detection. But my talk today is focused on the lazy strategy, do detection, and after that, we do adaptation. So we need to, people will say how to do this detection. So we need to understand when you do detection, you need to have a time window, right? So in time t and time t plus 1. And you compare the two windows and to say any drift happened. We don't give much details, but I just for each part gave some basic ideas. So under our lazy strategy, we have two methods to do concept drift detection. One method is to check this prediction accuracy. If your prediction accuracy significantly reduced, then that's performance is getting worse. That is possible this drift happened. So you can see here, significant drift, significant this reduced. So that is one method in this area, and to just use this accuracy reduced or not. Second one, this one is from statistical point of view. And this do hypothesis test. So you can say the distribution has been significantly changed. Oh, this this example is a two sample test. This in T1, this in T2, or time T or time T plus. That's two main methodologies used for drift detection. For drift understanding, we use classification as example, and we have decision boundary. Then it's in time t. And in time t plus 1, and we say this, the decision boundary has been changed. And if you just use a normal way, you can say here the middle is a decision boundary concept drift area, right? Because the two decision boundary between them. But if you do more work, then you can consider actually only changed in such little area. That's what we call this drift area, drift region. So that means if you want to change your model or do model update, you only need to consider that is the change area. So don't need to over this look the whole change from the two boundary. And that is a drift understanding about where. If you are interested about how, what, I can give you more these references. Because that is important, just to reduce our estimation of drift region. About drift adaptation, as I mentioned before, 3 ways. One is originally that's originally model, and we return model. Just forget about today's previous one. But if you do this one, you must remove these outdated instances first, then return a new model. And for the second, this very popular one, just fine tuning. And this one, you can do data updating, or even not necessary. Some new algorithms don't do it, even our algorithms. And then you just use, for example, incremental learning. Then another one, just the example method built this the model, but more hard work in this area is to make a good weightings for each model. So that's a 3 part. For each part, we have some methods. I just tell you some applications. One is about a bank credit assessment system. So we know customer behaviors change over time. Particularly if some person is lost a job, then the assessment model couldn't be used. Because for customer data, you have some certain factor, age, so on, no change. However, you have some uncertain factor, right? For the occupation, for example, that's uncertain this factor. And uncertain factor could have a drift. When have a drift, then your model generated to evaluate this particular credit doesn't work. So you need to, you can use concept drift adaptation technology and to do a real-time update. The second application is about pricing. So for this market price, we know this also changed very often over time, and a lot of factors, increase rates and so on, many factors. And but those factors, if you collect all the factors, you do prediction, that's okay. However, it's a bit too late because when you get the factors, it's already not real time. If you want real-time concept drift detection, we talked about today in the stream, mainly it's real-time or nearly real-time. So that's if you use concept drift, can do this can detect some potential change and in advance. So that is another application. Now we talk about the personalization. As I mentioned, we have lots of data and lots of products, and customers would like to have a personalized recommendation. And how to do this way? First, we understand what is personalization. So personalization, this customer just have a feeling is a one-to-one, just like you call someone, someone talk to you, that's one-to-one service. If everybody go to web page and say the same results, then one-to-many, not a one-to-one. But personalization is different from customization. If you take a phone call and to say, would you like to buy a flight ticket, or would you like to make a change? Then you say one, you click one. Then say, if you're old customer, please press 1. If you're new customer, press 2. Then you press 2. Then say, if you come from Sydney, press 1. If you come from New Zealand, press 2. Those are not personalization because you know what will happen. It's called customization. Personalization, people normally passive. And the system doesn't need to ask you many questions and directly identify with your very little information and use algorithm to work out and your preference or what you need or what your requirement. The reason is they use the algorithm. They can do some use some predefined user and to use, for example, user X and user Y, both love product A and B. Say A and B, and because X loves C, so we say Y will love C as well. So use such kind of ideas to generate personalization. At the moment, the best way to implement e-service personalization is recommender systems. So recommender systems aim to provide right information about services to right user at the right time. So 3 rights: right information to right user at the right time. And we have a number of different types of recommender systems. For example, content-based, collaborative filtering-based. The main idea is we have this, we use collaborative filtering based as example. We have some user item metrics, okay? Number of users, number of items, we collect a number of data already. And this, we have this some for the user metrics, including your this purchase history, including your renting and so on. Then this, we have a number of users here, number of items here. Then this, for example, we know user is a red user, just log in, and we immediately generate item E to say, I think item E is your preference or is suitable for you, this finance product. That's the basic idea. Then if you say this blue person is the same, has the same experience as the red person, then maybe C2 is similar as E, that you can this generate a recommendation C2 to this person. That's it's a very basic idea. In the last 20 years, recommender system have been developed a lot. In my group, we have developed multiple criteria-based recommender system, trust-enhanced recommender system, social network-based, and tag-aware-based, and fuzzy set enhanced-based, and tree similarity-based group recommender system, and cross-domain recommender system, and user interest drift, and also recommender system visualization. So I just quickly introduce 4 of the 10. One is a social network. The idea is when you have a new user, you don't have any information about the user, then what you need to do? So we can use a social network because that new user we call cold start problem. Then this how to deal with that one. We can use some data get from social network. That is social network-based recommender system. This tree structure one, actually we got this idea because about 10 years ago, I worked with one telecom industry. And I realized that the recommendation not about one book, not about this one clothes. Now it's a package. Similar as a bank, it's a package. And for example, telecom package one, they include fixed line and mobile and this broadband, because this recommendation not only for one single person, it's for a small company, like a hotel, for example, or a supermarket. Then they have lots of mobile phones, some international calls, some local call, and lots of fixed lines and so on. So in such case, you need to consider similarity. We know similar users and similar items. Those are the 2 key techniques in recommender systems. But now how to compare 2 trees. Then we developed these new algorithms for recommender systems to deal with tree similarity. Then we can use this one. We have been using this one in this these applications, and to deal with package recommendation, personalized package recommendation. The third one is group recommender systems. Quite often, people would like to have recommendations, not one person, it's a group. This could be a randomly built group or could be people know each other, some fixed groups. So how to generate a recommendation to maximize the satisfaction of all group members. So one way is we can aggregate this individual profile first, then generate a group profile, and then generate a recommendation. Another way is we generate individual profiles and individual recommendations, then we aggregate individual recommendations. That's two main models, but lots of algorithms in details. The aim is clear, is to maximize the satisfaction of all group members in large. This is quite recently we worked on about cross-domain recommender systems. And sometimes you want to generate these recommendations for new product. You have very, very little data available, very little. So not enough to generate a recommendation. But at the same time, you have a similar domain. For example, there's books and movies. And then can we use the similar domain, lots of data available? Can we use the knowledge generated by moving the similar domain and transfer the knowledge to use for the current domain we call target domain, which doesn't have enough data to generate a recommendation? Yes, so that's what we call cross-domain, this recommendation. Currently, we have this solve the problem, but currently we solve a more challenging problem. You have target domain for new product. You don't have much data available. And you find some similar domain, but also not enough data to generate knowledge for transfer. Then you can find a number of source domains, okay? You have source domain A, B, C, D, and some similar, some not similar, but together they have more data available to generate the knowledge, and the multiple source domain together the knowledge transfer to target domain. So we fully use the transfer learning algorithms, the transfer learning ideas into recommender systems. And that is another development of transfer of a recommender system we call cross-domain and transfer recommender system. So applications, I have there's one application in customer churn prediction. We know these banking systems, lots of customer churn happened, similar as telecommunications. And you can change one plan to another plan. And also the user profiles can be changed. And say what we need to do, and we need to fully consider the change and to help us generate personalized recommendation. And this way for customer churn prediction, actually we combine concept drift. That means this, we mentioned the first part, concept drift, and recommendation, personalization combined together. So identify the drift, the changes of customer record. And then there's update the model, and then is identify the groups of customer churn groups, then modify the recommendation strategy. So that is the basic area. Basically, there's a way from the raw data, get a targeted data, and those ones is your customer churn data we use possible, then we generate these models. Also, we have prediction about who will churn in short term, high risk, middle, or low, and then for those people, we generate personalized recommendation. Different types of people, different personalized recommendations. And so, as I mentioned about recommendation for tree structured, that's mainly for small and medium businesses, because every package has a number of mobile phones, fixed lines, and so on, so on. That's very important, this part. This one can be used for existing users, small businesses, also can be used for new users. So that is an example with the system we developed, and about the one package. And this one package recommendation 1 and the recommendation 2, and for quite a number of different types of products or services. And then there's if you want to know more details for recommendation 1 or 2 to finalize, then we can see all the details. And finally, the system will generate a PDF document. When you select, say, I would like a recommendation 1, then this will generate a PDF document, maybe 10, 15 pages, whole package. Okay, so my talk today, we covered 2 these topics, but linked directly. One is about prediction. And we consider the situation is in concept drift situation. That means in data streams, and data distribution keeps changing, very fast changing. And if you don't consider concept drift, then you still use the old model to do prediction, then this your decision made could be a disaster. And also, if you always train a new model and you don't know when is the time to update a model, that also cannot get accurate prediction in the real time. So our concept drift idea is to help prediction in data stream situation and keep this always updated model. A lot of research have proved that concept drift is the root cause of accuracy of online learning prediction, because we want to do real-time online machine learning. Then personalization is an important finance service technology and requirement. So recommender system based this recommender systems will provide those personalized services. Thank you very much. This is my talk today. Thank you.
Thank you, distinguished Professor Lu, for your comprehensive presentation on prediction and also personal recommendation. I have a question from the audience, so hope you can answer some of them maybe. So the first one is about the challenge around the trading of coverage for accuracy. You minimize the effect of both noise and the concept drift.
Yeah, very good, very good question. The noise and the concept drift, exactly that's 2 things. So there's some technologies have been developed just to deal with this noise and concept drift, to make sure that's noise, not drift, or this is drift, not noise. And it is, I cannot give you this some algorithms here, but as I can tell you, this is indeed the challenge issue, and indeed you need to make sure that it's a noise and it's not drift, or drift, not noise.
Okay, so basically, is I guess there's a balance for the.
Not a balance, not a balance, not a balance. So if you can identify that it's a drift, that's a drift, and if you identify that's not drift, just the noise, then there's that you can still use previous classifier to continue your machine learning.
So you have the way to find that.
Yeah, we have this algorithm to do it. Yes.
Okay, great.
But particularly when you do adaptation, even you identify that it's a drift, then when you do adaptation, you still need to remove this noise.
Thank you for answering. Okay. There's a second question, probably not so close related to your presentation. They say any short on applying symbolic machine learning directly to temporal prediction. Applying symbolic machine learning directly to temporal prediction.
Basically, yes, you can use some simple machine learning algorithm.
No, they say symbolic machine learning. Symbolic machine learning.
Okay. Yeah.
No.
So this you mean not need to be in data streams, right?
Okay. Yeah. Okay. Yeah. That's good. That's the two questions we select to ask you, and thank you again for your wonderful presentation.